Today we're building something truly unique, an AI-inspired neural network animation. This effect will simulate neurons firing, creating a stunning data visualization that could be used for AI apps, futuristic dashboards, and interactive UI elements. If you want to add mind-blowing effects to your Flutter apps, stick around till the end. Let's get started. First, create a new Flutter project. Once the project is ready, open it in your favorite code editor, navigate to main.dart, and set up a basic structure of Material app. Create a new file named neural-network-screen.dart. First, we have this class called neuron. Now, in the context of a neural network, a neuron is like a fundamental building block, right? In this code, this neuron class is really simple. It's designed to represent a single neuron in our visual animation. We see two things here, position and connections. Offset is basically a class that holds a 2D point. So, each neuron object will have a position, which determines where it's located on our animated screen. This is crucial because we need to place these neurons somewhere, right? Then we have a list of neurons. This is a list that will hold other neuron objects, and it's named connections. This suggests that neurons in our network are going to be connected to each other. Just like in a real neural network, neurons form connections. In our visualization, this list will store references to other neurons that this particular neuron is connected to. Initially, it's an empty list, meaning when we first create a neuron, it's not connected to anything, but we'll see later how these connections are established. And lastly, we have a constructor. This constructor takes one argument, position. So, when we create a neuron, we must provide its initial position. Alright, that's the neuron class. Pretty straightforward. It represents a neuron with a position and a list to hold its connections to other neurons. Now let's move on to the next class, Neural Network Painter. Notice that it extends CustomPainter. In Flutter, CustomPainter is a really important class when you want to draw custom graphics on the screen. Think of it as your canvas and paintbrush in Flutter. So, Neural Network Painter is responsible for actually drawing our neural network visualization. Let's see what it holds. It has two properties, neurons and time. Neurons is a list that will hold all the neuron objects we want to visualize in our network. So, when we want to draw a network, we'll give this Neural Network Painter a list of neurons. Time is a double-type variable named time. And you might be wondering, why time? Well, remember we're building an animation. Animations usually involve changes over time. In this case, time is going to be used to make our connections between neurons wiggle and animate. We'll see exactly how in a bit. Now let's get to the heart of the Neural Network Painter, the paint method. This is the method that gets called by Flutter whenever it needs to draw something on the canvas using this painter. It takes two arguments, canvas and size. Canvas is our drawing surface. Think of it as a blank sheet of paper where we can draw. The canvas class provides methods like draw circle, draw line, draw path, etc. to actually draw shapes. Size tells us the size of the area we have available to draw on. It's useful if you need to make your drawing responsive to different screen sizes. Though in this code, we might not be directly using size for responsiveness in a very detailed way, but it's there if we needed it. Inside the paint method, we are creating two paint objects. In Flutter, paint objects define how things are drawn, things like color, style, stroke width, and more. First, we're creating a paint object named Neuron Paint. We're setting its color to yellow. So, when we use Neuron Paint to draw something, it will be yellow. We can guess this Neuron Paint will be used to draw the neurons themselves, probably as yellow circles. Similarly, we are creating another paint object named Connection Paint. We're setting its color to blue accent. Alpha controls the transparency. A value of 1 is fully opaque, 0 is fully transparent. 0.4 means it's going to be slightly transparent, allowing things behind it to be a little bit visible. Blue with a bit of transparency, nice color for connections. Stroke width sets the thickness of lines or outlines. Here, it's set to 2, meaning connections will be drawn with a thickness of 2 pixels. So we've set up our styles, yellow for neurons and semi-transparent blue, slightly thicker lines for connections. Now let's look at the drawing logic inside the paint method. We have a nested loop structure. The outer loop is iterating through each neuron in the neurons list that we pass to the Neural Network Painter. Inside this outer loop, the first thing we do is draw circle. This is drawing a circle on the canvas. We have 3 arguments here. Neuron.position, remember, each neuron has a position, an offset object. This is where the center of our circle will be. 10. This is the radius of the circle, so it will be a circle of radius 10 pixels. Neuron paint. This is the paint object we created earlier and set to be yellow. So, we're drawing a yellow circle at the position of each neuron with a radius of 10. This is how the neurons themselves are visualized, as yellow circles. Next, inside the outer loop, we have another loop, for our connected neuron and neuron dot connections. For each neuron, we are now iterating through its connections list. Remember, neuron dot connections holds a list of other neurons that this neuron is connected to. Inside this inner loop, we have the logic to draw the connection between the current neuron and each connected neuron. We're using a path object here. In Flutter, paths are used to draw complex shapes, including curves. Path.moveTo starts a new subpath at the given coordinates. Here, we're starting at the position of the current neuron. Path.quadratic Bezier 2. This is where we draw a quadratic Bezier curve. Bezier curves are smooth curves defined by control points. A quadratic Bezier curve is defined by a start point, an end point, and one control point. Let's break down the arguments of quadratic Bezier 2. The first two arguments define the control point of the quadratic Bezier curve. The first argument is the average of the x-coordinates of the current neuron and the connected neuron. Geometrically, this is the x-coordinate of the midpoint between the two neuron positions. Similarly, the second argument is the y-coordinate of the midpoint. But we have something added to these midpoints, sine time and cosine time, multiplied by 20. Here's where the animation comes in. These are being added to the x and y coordinates of the midpoint to get the control point. Remember that time is a property of Neural Network Painter. As time changes sine time and cosine time, values oscillate. Multiplying by 20 scales up this oscillation. Using sine time for x and cosine time, for y is going to create a circular motion, or at least a component of circular motion, in the control point's position as time progresses. This means the control point of our Bezier curve isn't fixed at the midpoint, but it's moving around the midpoint in a somewhat circular way as time changes. This movement of the control point is what causes the Bezier curve, which represents our connection, to wiggle and animate over time. It's a clever way to add a dynamic, organic look to the connections. Finally, after defining the path, which is our quadratic Bezier curve, we draw it on the canvas using canvas.drawPath. We use connection paint, which we set to be semi-transparent blue with a stroke width of 2. So, the connections will be drawn as these animated, blue, slightly see-through curves. After drawing all connections for a neuron, and after drawing the neuron itself, the outer loop continues to the next neuron, and this process repeats for all neurons in the neurons list. After the nested loops are done, the paint method ends. This completes one frame of drawing our neural network. Then we have should-repaint method. This is another method of CustomPainter. Should-repaint is important for performance. Flutter calls this method to decide if it needs to repaint, the canvas. If should-repaint returns true, Flutter will call the paint method again to redraw. If it returns false, Flutter will skip redrawing, saving resources. Here, it's always returning true means. In this case, we want the animation to run continuously, so we always want to repaint to reflect the changes in time, and thus, the animation. For a continuous animation like this, always repainting is often what you need. Alright, we've gone through the neuron class and the neural network painter class in detail. We understand how neurons and connections are drawn, and how the animation is achieved using the time variable and Bezier curves. Now, let's animate this network by updating the neurons and connections dynamically. Starting with Neural Network Screen. It's a stateful widget. Inside Neural Network Screen, we have Neural Network Screen State. It uses single ticker provider state mixin. This mixin is essential for creating animations in Flutter. It provides a ticker provider, which is needed by AnimationController to drive animations at a consistent frame rate. Inside Neural Network Screen State, we have two important properties, controller and neurons. AnimationController is the heart of animation in Flutter. It manages the animation's progress, duration, and more. Neurons will hold the list of neuron objects that we'll be animating. Now let's look at initState method. This method is called when the state object is first created. First, we're creating our animation controller. We set the duration to 10 seconds. The animation cycle will last for 10 seconds. VSync needs a ticker provider. By using single ticker provider state mixin, our neural network screen state class becomes a ticker provider. VSync is important for performance and battery life, especially in animations. Repeat method is called on the animation controller. This makes the animation loop continuously. After it reaches the end, it will start over from the beginning. Next, we initialize neurons. List.generate is a convenient way to create a list of a specific size. Here, we are creating a list of 8 elements. The second argument is a function that's called for each index, from 0 to 7 in this case. For each index, we're returning neuron object. Inside the neuron constructor, we're creating an offset using random.nextDouble into 300 for the x-coordinate and random.nextDouble into 500 for the y-coordinate. It will give us random x positions between 0 and 300 and random y positions between 0 and 500. So we're generating 8 neurons, each with a random position within a 300 by 500 area, approximately, depending on the screen size, but these are relative coordinates. After creating the neurons and setting their positions, we set up the connections. We loop through each neuron in our neurons list. For each neuron, we're taking all the neurons from neurons list, creating a new list using list.from, and then shuffling this new list using shuffle. So now we have a shuffled list of all neurons. Then we're taking a sublist from the shuffled list. Random.nextInt will give a random integer between 1 and 3, inclusive. Sublist takes elements from index 0 up to, but not including, the given length. So for each neuron, we are randomly picking 1, 2, or 3 other neurons from the shuffled list to be its connections. This ensures each neuron is connected to a random number, 1 to 3, of other neurons from the network, and the connections are somewhat random. So, in init state, we've initialized our animation controller, created 8 neurons with random positions, and randomly established 1 to 3 connections for each neuron from the set of all neurons. Next, we have dispose. Dispose method is called when the state object is being permanently removed from the widget tree. It's important to release resources here to prevent memory leaks. We need to dispose of our controller using controller.dispose. Finally, let's look at the build method. We're returning a scaffold with a black background. The most important part is Animated Builder. Animated Builder is a very useful widget for animations. It rebuilds only when the animation is listening to, in our case, controller, ticks, making it efficient. We're telling Animated Builder to listen to our controller's animation. The builder function is called every time the animation ticks. It needs to return a widget that will be rebuilt on each animation frame. Inside the builder, we are returning a CustomPaint widget. Think of CustomPaint as a widget in Flutter that provides you with a blank canvas to draw on. It doesn't draw anything itself inherently. Instead, you tell it what to draw and how to draw it using its properties, primarily the painter property. The painter property is where you provide an object that knows how to paint. It expects an object that is a subclass of CustomPainter. And in our code, we've created exactly that, our Neural Network Painter class. So we are creating an instance of Neural Network Painter right here. For the first argument, we are passing our list of neurons. In the second argument, we are passing controller.value multiplied by 2 and pi. 2 multiplied by pi is approximately 6.283. It represents a full circle in radians. So, the second argument is calculating the current time in radians for our animation based on the progress of the animation controller. This calculated value is then passed as the time parameter to the Neural Network Painter. The Neural Network Painter then uses this time value in its paint method to animate the connections using the sine and cosine functions. In essence, we're feeding the current animation time to our painter, and the painter uses this time to draw the animation frame. As the animation controller progresses, controller.value changes, which in turn changes the time passed to Neural Network Painter, causing it to redraw with slightly different connection curves on each frame, creating the animation effect. Finally, we set the size property to size.infinite. The size property of Custom Paint determines the size of the canvas that the painter will draw on. By setting it to infinite, we are essentially making our neural network visualization as large as it can be within the constraints of the screen and the padding we've applied. We can see the stunning neural network animation in the app screen, with yellow neurons and blue connections. You can play around with different properties, values, and painter class to customize according to your requirements. And that's a wrap. We just built an incredible AI-inspired neural network animation in Flutter. Want to learn more Flutter animations? Check out other Flutter animation videos on this channel. Until next time, keep fluttering.